Hello everyone and welcome to today's graph reading group.
Where we will be discussing the expressive power of geometric graph neural networks.
Hi everyone, I'm Chaitanya and this is Simon, and we're both PhD students at the University of Cambridge, supervised by Pietro Leo, and we'll be presenting our work on the expressive power of geometric graph neural networks, which is done in collaboration with Chris Bodnar, Taco Cohen, and of course Pietro. And I'll let Simon start.
Awesome. Thank you, Chaitanya, for the introduction. Thank you all for being here, whether it's morning or afternoon. We have the pleasure of talking about our work on the expressive power of geometric graph neural networks. And I'll start with a quick primer on why that's interesting. Let's see if the slides flip. Can you see the slides flipped? Just to confirm that you're following along. Yeah, perfect. Okay, so what are essentially geometric graphs, geometric graph neural networks? Where are they relevant? The field of geometric graphs is essentially where geometrical information meets relational information. And here are a couple of examples where that happens. That happens in lots of areas of chemistry and physics, small molecule simulations, proteins, but also, say, for example, in multi-agent robotic simulations, as Amanda Prorok in Cambridge here does, for example. And to just give you an idea of where geometric graph neural networks are used, they can be used, for example, in predictive tasks, both for classification or regression. They can be used, or they've successfully been used, also by Hannes in particular, in diffusion models, where essentially you use them to predict noise. There was also RF diffusion and chroma, which used geometric graph neural networks very prominently for protein design. And you can also use them in sort of an autoregressive setting where you simulate, say, the dynamics of molecules. And so with that, I hope we've established that geometric graph neural networks are interesting and worth studying, both because they cover a lot of domains and they're useful for many different tasks. And over the last couple of years, 5 years, there's been some sort of explosion of geometric graph neural network architectures. And you can see here categorized by two flavors, whether they pass around invariant or equivariant features. We'll explain some of these models in a bit more detail slightly later on in the talk. But this slide is just to show you that there's been lots of architectures, lots of fantastic model building. And we were kind of coming and starting the PhD as first-year PhD students. We were asking the question, oh, can we kind of understand them in some sort of unified framework? Can we say, what can this model do that another one cannot? Can we have some sort of characterization of geometric GNN land? And to give you an idea of the types of geometric GNNs we're going to talk about in this talk, I thought I'd quickly draw up an informal taxonomy. So we distinguish between what we call canonical reference-based geometric graph neural networks and reference-free graph neural networks. Canonical reference-based graph neural networks are essentially just graph neural networks which predict some sort of canonical reference frame. They could either use it, for example, to predict a global reference frame based on the full structure, or local reference frames based on each neighborhood, essentially predict, X, Y, Z axes, for example, in three-dimensional space, and then use these to guide their message passing. Or we could follow a reference-free approach, which many of the other prominent graph neural networks follow. And our focus in our work really puts an emphasis on the reference-free approach. So that's essentially where our exploration holds. So message passing, where we don't actually want to first rotate our graph or our neighborhoods and canonicalize them to some sort of reference frame, but we want to take them in whichever reference frame they're given. And to give you the main results of the paper ahead of the time, and then we'll go into details how we get to them, the key takeaway really is better understanding the design space of reference-free geometric graph neural networks. And to characterize this design space, we use three main axes. The axis that goes out of the page, out of your screen, is depth. And I think that's more or less self-explanatory. So essentially how many layers of a particular graph neural network layer do we stack. And then the second axis here, the y-axis, is what we call the body order axis, the many-body axis. And that essentially tells us how many nodes factor into the computation of a single, essentially, feature. So, for example, distances are a two-body feature because it requires us to look at two nodes to calculate the distance. Angles would be a three-body feature in this terminology, because we would have two nodes pointing outwards and one at the apex, which we use to calculate angles. And so we can essentially build various graph neural networks by increasing along the many-body axis, or we can also essentially vary the tensor order of the features. And what do we mean by tensor order? By tensor order, we mean essentially how do the type of features that are passed around in the graph neural networks transform. So scalars do not transform under transformations of the ambient space. For example, the atom type would not transform. L equal to 1, or what are here called Cartesian tensor features, or essentially vector features, would rotate accordingly with the space. And then there's also higher order geometrical features. For example, array would be a feature which would rotate around with space accordingly, but would be a second order, or could be decomposed into a second order high tensor feature. And the three takeaways here is that if we restrict ourselves to layers which only pass around invariant messages, so scalars colored here in green, then that has a limit on the expressivity in this reference-free framework, in the sense that we can only, or we cannot distinguish graphs which are identical in their one-hop signature. And Chaitanya will explain in more detail what that means. The second key takeaway is that if we use equivariant layers, so essentially if we allow ourselves to go beyond the green colored nodes to blue and red to higher order tensor features, then we can actually distinguish larger classes of graphs. And the reason for that is that we can propagate geometric information beyond local neighborhoods. So said very simply, we can say how do different neighborhoods glue together in which orientation, and propagate that information across the graph. And finally, the third takeaway is that higher order tensors and higher body order in the scalarization really allows us to get more powerful graph neural networks than using essentially lower versions of on these axes. With that, I'll pause for, or do we take all questions at the end? Sorry.
I think
Should we?
here the ethos is to ask questions along the way, right? So
Ethos
we do encourage.
Absolutely. Always.
Yeah.
Cool.
I've got a question, actually. Let me just raise my hand.
Yeah, please.
Could you go back to the last slide?
Last slide, yes. Ooh, there we go.
So can you call the bullet points again?
Yes. There we
Yeah,
go.
so this part right here, where you're talking about the second part, the equivariant layers, you're saying that what's happening is that what's interesting about having equivariant layers is that there's like these local neighborhoods, which makes these clusters that look like they're sort of like isolated with each other. But what's happening what you can do with the equivariant layers is that you can sort of like, in a sense, sort of like zoom out in a way that you can actually see that those two local clusters are actually part of one larger cluster. Are you saying that that's what you can do with equivariant layers where you can't do that with invariant layers?
Sorry, yeah, I wasn't completely clear on that. We will explain it in more detail later, and we'll have some animations which show that. The key point is you can actually propagate, even within invariant layers, information of different neighborhoods.
Yeah.
What you can propagate is how those neighborhoods are oriented with respect to each other. So the relative orientation of the neighborhoods, that's where the equivariance really features. Does that make sense?
Cool. I think that makes more sense now. Yeah.
Makes more sense. Okay, lovely. And there'll be images in Chaitanya's section of the talk, which hopefully make that even more clear. Any other questions? And thank you very much for the question, by the way, for clarifying this. Otherwise, I'll very quickly do a tiny little background section on graph neural networks and geometric graphs, just to make clear we're all using the same definitions, and then we'll get into how do we get to these results and to these intuitions. So very quick recap. What's a graph? Essentially, it's a collection of nodes together with some edges, which I think everyone in this reading group is very familiar with. Usually, the features we have in our terminology would be scalar features, because these graphs are not normally embedded in a space, but when we do take them into some ambient space, those features would not normally transform. Essentially, there's no notion of ambient space in normal graphs. So there's no notion of how the features transform. So we've got our graph, we've got edges and nodes, and then we can do message passing graph neural networks by essentially compiling a message from node J to node I based on some messaging function F, which is essentially up to definition of your model. We aggregate those messages, and the double brackets here mean that we aggregate them as a multiset. So we only know how many messages of which type we get, but we don't actually know which message came from which exact node. And that comes from the requirement for permutation invariance, or permutation equivariance in graph neural networks. And then we update our features based on the messages, the aggregated messages that we've received from all the other nodes. And so a different way of looking at this is essentially if we unroll the computational tree for every hopping step that we take, then the one hop neighborhood would be what you see here essentially in layer 1. In layer 2, you get messages from all your 2 hop neighbors. In layer 3, you get messages from all your 3 hop neighbors, and so on. So this is the classical graph neural network setting. And how does that transfer to the geometric setting? The difference in the geometric setting is that our graph is now embedded in some sort of ambient background space. Sorry, was there a question? No. Okay, sorry, I thought I heard some noise. So our graph is now embedded in some sort of ambient background space. Could be d-dimensional. In our case, for most applications, it's 3-dimensional space. So for example, a molecular graph might be embedded in 3-dimensional space. And then we have features, scalar features, so features which do not transform if we transform the coordinate axis of that space. For example, which atom type each node is identified with. And then we also have features which actually do transform as we change or rotate our coordinate system. And that would be, for example, the exact coordinates at which each of the nodes is located, or say velocity vectors with which those nodes are moving, and so forth. So in addition to the edges and the nodes, we also now have vector and velocity features. And oh, there we go, yeah. And what does that mean? What bearing does that have on message passing? Well, the big difference between what we previously had is there was no notion of how features transform under transformations of the space because the graphs were not embedded in any space. But now the graphs are embedded in space. And so these different types of features are really, in a sense, a different classes of objects. So the atom type does not transform if we rotate. You see here, essentially, the scalar nodes do not transform, they stay the same. Whereas the vectors or coordinates actually rotate along with the system. So if Q is a, say, rotation or reflection matrix, then under a rotation of this graph in 3-dimensional space, also we need to rotate the coordinates at which the nodes are located, or the velocities with which, in the direction of the velocity in which they travel. And likewise, the same holds for translations. And what that means is that really gives us some constraints on how we update those features if we choose to update them. And these are essentially two philosophies of geometric graph neural networks. One way of updating them is to say, okay, I will keep around my vectors and my coordinates, for example, so my vector features or higher order tensorial features, but I will not update them from one layer to the next. I will only compute the scalar from them, for example, the distance or the norm or an angle, because this is invariant. And then I will only update the scalars in every layer. And that's what we call, that network function would be an invariant function. It doesn't matter whether I take my graph, compute these distances, and then do the message passing layer, or if I rotate it first and then do the same. On the other side, there would be equivariant layers, and equivariant layers choose to also update higher order geometric features, for example, vectors. And if we do that, we need to make sure that it doesn't matter whether we first rotate our graph and then update the features, or whether we were to update the features and then rotate the graph. We would need to arrive essentially at the same position. And that's what this picture here specifies. And that gives rise to geometric graph neural network message passing, where we can have essentially scalar messages or vector messages which update the scalar channels or vector channels or higher order tensorial channels of the features. And then, I mean, the equations essentially are the same as before, purely that the only difference is that we now have more features that we take care of. So this was a quick primer on the definitions of geometric graph neural networks, invariants and equivariants. Let us quickly take a browse through the design space, and then we get of a few of the models we mentioned to give you a flavor, and then we go into why we need to characterize those. So let's start with the invariant geometric graph neural networks, this first box here. And as I said earlier, they only update the scalar features by first scalarizing the geometric information. The first example, or the simplest example, would probably be Schnitt, where we take the geometric information, the coordinates, and essentially just compute the distance between two nodes and concatenate that into our message function. And this is rotationally invariant, or invariant to translations, because we're only using the distance. So if I rotate a certain structure, of course, the distance between all the nodes stay the same. If we go one body order higher, if we look at angles as well, then we arrive at an architecture like DimeNet. And the idea here is that we're not only using distances, but we're also using angles in our message passing. And you can see this here expressed in the message function. And then you can go higher, you can add torsion angles, etc., etc. You can add higher order, essentially, scalar features. This was invariant networks. Now we go to equivariant graph neural networks, which also, the difference is they also update, say, vector features or later on higher tensorial features. And an example of a equivariant graph neural network would be Pane. And the crux here is that we update not only the scalar features with a scalar message, but we're also updating the vector features, as you can see here. And in this particular case, we've got two options of updating the vector features. We can essentially gate them and add the vector features attached to the nodes, or also add a scalar product with, or gate them and add the coordinates. So these are the type of vector features that are used in Pane in particular. And then on the very far end, if we not only use scalars and vectors, but if we also go to higher order tensorial features, then an example of this would be tensor field networks, where we allow ourselves to also use quantities which transform in more complex ways than simple vectors or scalars. And for reasons of time, I won't go into it now, but if you do have questions, we're happy to go into this in more detail a bit later. So we've seen a couple of examples of graph neural networks. We've defined what graph neural networks, geometric graph neural networks are. Now the question is, how do we categorize all of this zoo of models, and how are they different from one to the other? And why would we even want to do that? And as a motivating example, I encourage you to try and distinguish these two local neighborhoods centered around the gray node, purely based on distances and angles. And you can see all the distances here are the same, and all the angles, the histogram of all the angles are the same. And the crucial point here is that we are only allowed to look at the unordered set of distances and angles because of the permutation invariance in the aggregation step of graph neural networks. And you'll see that even though these are two different local neighborhoods, they are actually having the same signature in terms of distances and angles. And this goes beyond the problem of single neighborhoods. Oops, there we go. This goes beyond the problem of single neighborhoods. These two structures, these two graphs are exactly the same based on their distances and angles in the local neighborhoods. And so if we perform message passing, we would never actually be able to tell these two structures apart. And the real difference of essentially how to distinguish them is that how these local neighborhoods are oriented with respect to each other. And the point of view that we take in our paper is how do we characterize which structures a particular graph neural network can distinguish or not distinguish in order to study its expressivity. And here I'll hand over to you, Chaitanya, to take us through the results.
Yeah. So as Simon said, the central idea is to formalize this problem of geometric graph isomorphism, especially in the context of all these geometric GNNs that we're studying. So just to recap, right, what is graph isomorphism? Well, the graph isomorphism problem asks the question of whether two graphs are the same but drawn differently. Sorry, second. So two attributed graphs are isomorphic if there's an edge preserving bijection, if there's a relabeling of the nodes such that you get the same adjacency structure. And the Weisfeiler-Leman algorithm is a test for determining whether two graphs are isomorphic or not. There's a rich history of work on graph isomorphism and algorithms to detect it. Specifically, the WL test is a test which updates node coloring. So every node in your graph is assigned a coloring via the concept of injective coloring functions. So injective functions basically mean that you assign a unique color to each unique neighborhood pattern. So for example, here, right, you'd start with assigning a color to every node. In this case, all nodes have the color gray since we don't assume anything about their features. And then at each iteration of the WL algorithm, you will recolor your nodes using this function hash, which is the injective map that we just described. It takes as input your current color and the set or multi-set of your neighbors as colors. And for each unique input pattern, it'll assign a unique output. So the algorithm progresses iteratively and you recolor your nodes. So for example,
Chaitanya.
This goes to, sorry, go on.
Chaitanya, Simon, we're in the Learning on Graphs and Geometry reading group.
Okay. So
we know WL.
Okay.
we know what equivariant means and so on. But yeah.
Okay. No, you're right. Let's go over this fast. So let's go to the main content. So yeah, this test goes iteratively and you get a histogram of colors, and that color allows you to tell whether graphs are isomorphic or not. And in this example, WL actually fails, which is interesting because there are lots of failure cases of WL. But for most practical purposes, people claim that WL is good enough. And why is that important? That's important because WL is an upper bound on graph neural network expressivity. So graph neural networks can be as powerful as WL at graph isomorphism, and they'll fail at all the same things that WL also fails at. And this is interesting because we can now study the theoretical limitations of GNNs, and then we can design architectures to improve those theoretical limitations. And this is a very hot area of research. The key thing here, though, yeah, go on.
Still, thanks for going into them because I think you explained them super nicely, like these things like WL and equivariance. Also very fancy slides. So I think that will also be cool to have a YouTube video. But here I would probably also want to say, right, that there are higher order WL tests, and maybe these also inspire then GNNs that are able to distinguish graphs and be more powerful than the standard GNN, so to say.
Yeah.
But I mean, let's just be careful with saying upper bounds GNN expressivity, because I mean, maybe people also see a graph transformer as a GNN or just a neural network that processes graphs. So maybe we can't really say that it upper bounds GNN expressivity.
Yeah, I guess
But
the
I
most,
think we all know what you mean.
yeah, like the more precise statement is regarding message passing GNNs, which, you know, don't use positional structural encodings or unique node IDs, right? Of course, you're right. Thanks for catching us on that. But then the key research gap even with all this progress is the theoretical tools for normal GNNs, such as this WL framework and WL hierarchy, are actually inapplicable for geometric graphs and for geometric GNNs. This is due to the presence of the physical symmetries that Simon described. This is due to the fact that features in geometric GNNs actually carry physical meaning and need to respect certain properties regarding their equivariance. And that's where we formulate this this problem of geometric graph isomorphism, specifically in the context of the models we're studying. And this problem is essentially saying that two graphs are geometrically isomorphic is if you can superimpose them onto each other. There exists, of course, an attributed graph isomorphism, and the geometric attributes are equivalent. So once we formulated this problem, we can now talk about our framework, the geometric Weisfeiler-Leman test, which is a theoretical upper bound on geometric GNN expressivity. So trying to translate the success of the WL framework to the geometric setting and see what insights we can learn. The key intuition here for generalizing WL to geometric graphs is that both of these tests should be node-centric and based on the property of injectivity. So in standard WL, you have the notion of neighborhoods, which are actually these sets of invariant scalar features. In geometric graphs, you additionally have equivariant geometric features as well. So that's something extra we need to account for. Now, and the key ideas of node coloring, right? So these are these injective functions, almost like fingerprints of neighborhoods. So unique patterns being assigned unique outputs, unique colors. And again, we'd like to have the same thing for geometric graphs. So unique neighborhood should be assigned unique colors. But the key point is that we also have geometric information. So how a neighborhood is oriented. We know about neighborhood type, but we also need to account for how that neighborhood will be oriented in space. And that leads us to certain properties about the geometric WL test. The first one is the orbit injectivity of colors. So as we said, if two neighborhoods are the same up to rotation, their fingerprint or color should be the same. And this more formally just translates to orbit injectivity. So we should assign the same color to these two rotated versions of the same neighborhood. And this would by definition be an invariant coloring as well, an invariant fingerprint of your neighborhood. So then the other property is regarding preserving orientation. And this is important because as we said, satisfying property one, the coloring or the fingerprint will by definition lose information about the orientation because it's invariant, right? And that would mean that the test would no longer be injective, unlike WL. So in order to have an injective component to the test from one iteration to the other, we introduce auxiliary geometric information variables called GI for node I. And we'd like to make their aggregation injective as well as equivariant. So that leads us to initializing this test. We start much like WL by assigning a scalar node color to each node, which is some function of your input features. And additionally, and crucially, we'd have this auxiliary geometric information attached to each node. So the geometric information would be associated to a subgraph around each node and would be a nested sort of object, as we'll see in the next slide. So the first step, or the first operation in GWL, is to aggregate and gather local information in an injective manner. It can intuitively be understood as copy pasting. So, at every iteration of the test, you want to grow the geometric subgraph around your node. And you do this by sort of aggregating into your geometric object, GI, in a nested fashion. So you'd just keep this tuple and you'd grow this tuple at every iteration. And what this corresponds to is a sort of computation tree around your node I. So at each iteration, you can progressively view larger and larger geometric subgraphs around your node. To update your coloring. And as we said, the coloring function for GWL is an invariant I-hash function. So I-hash would just take the geometric information at that iteration and assign an invariant color to it. So you take the equivariant information and assign a color to it. For example, here, you can see that the central node would be assigned one color, and then the two nodes to its side would be assigned the same yellow color. And the reason for this is that when you look at the geometric subgraph centered at those two nodes, you can superimpose them, you can rotate them onto each other. So then you'd want to assign the same fingerprint to them, even though they're oriented differently. And GWL iteratively does this aggregation and coloring procedure. So for example, let's see how the test terminates. So of course, we want to discriminate two graphs, right? So we can take this example where we take these two graphs, which are obviously distinct, two geometric graphs, I should say. And we've just labeled what the corresponding nodes in each of the graphs are. And then when we show how GWL progresses, we can see that at the first iteration, the colors are the same for all the nodes in both these graphs. And as the test progresses, the colors change. And this is because, for example, in this case, all the one-hop neighborhoods among these two graphs are the same, but after one iteration, so in the second iteration of GWL, you then look at the two-hop neighborhoods at each node, and you can see that the two-hop neighborhoods centered at the blue nodes are actually different. So then in the next iteration of GWL, they're assigned a different color. And when the color histograms differ, much like WL, then the test says that the geometric graphs are not isomorphic. Now, yeah.
Can you just explain again, how do you start with your colors? And if you, for example, have vectors as initial features, I guess, and then how does your hash work?
Yeah, so when you start, right, your colors at the start would be just some function of your input scalar features, much like WL. So, you just initialize the colors with your scalar features, and you'd initialize your geometric information with your vector type information. So essentially there are two components of this test, one invariant part and one equivariant part. The equivariant part is responsible for gathering all the sort of local information and, you know, expanding the neighborhood that you look at. And then the invariant part colors that neighborhood, assigns a unique fingerprint or unique color to that subgraph around.
But how does the output, or how does the coloring depend on the equivariant features?
How does the coloring depend on the equivariant features? Well, the coloring is just a function of the geometric information at that iteration. So you can imagine, for example, that at this iteration, at iteration 0, at node I, you will be coloring this node based on this gray circle that we've drawn, just to represent what's stored in the geometric object GI. And well,
so like for example, here, if you have a canonical position in XYZ, then the difference would be because one would be like the delta Y would be negative, the other would be the delta Y would be positive in both cases, and you are able to distinguish them. Or for example, using torsion angles, like is this what you're trying to say? That this kind of information differ when you look at the two hop neighborhoods?
Yeah, I would say that for the purposes of the test, you actually assume that, you know, if any subgraph neighborhoods are different, then we assume that you can perfectly assign a color to them that would be distinct. In real models, right, this coloring step actually corresponds to scalarizing your local geometric information. So you sort of assume that you're sitting at your node I and you have all these vector features or vector messages coming into your node, and you need to scalarize them. You need to compute some invariant features out of them. So the simplest models use distances or angles. You could also use 4-body features or 5-body features, but essentially the higher body order of scalarization your model uses, the more local neighborhoods it would be able to distinguish or color uniquely.
Okay, but with 5-body features, you mean it, for example, so you mean that one node has 5 neighbors, or do you mean that we're doing multiple hops when you say 5-body features?
I think the former. So, you know, to compute a 5-body feature, you would need 5 neighbors to do so. Yeah,
but
because
they could come from different hops. So you would need 5 bodies, but they could come from different hops essentially.
Yeah.
What? Okay, but then how? Then your hash function doesn't take only the neighbors, the direct neighbors into account. It also uses multiple neighbors.
Yes.
Like no, it doesn't use multiple neighbors. It also uses neighbors of neighbors.
Correct. Yeah, it aggregates them as you hop along. Essentially, it accumulates the information from the neighboring neighborhoods.
Yeah, and it does so using GI. So, you know, at each iteration you grow your GI, and that's how you sort of accumulate information from multiple hops away. And then you color that information at each step as well.
Maybe just to say this is not an efficient procedure. So this is not computationally efficient. This is not meant to be implemented as a model, essentially. This is also not exactly how actual geometric graph neural networks do it. There you actually, you would add the features together into a channel, and implicitly you would pass them on through multiple layers. in a single channel where you aggregate them, say, for example, via summing. The idea is that we separate it here and that we keep it very simple by saying we're copy pasting and aggregating in order to disentangle what information is used for what. How you exactly build up this I-hash, for example, in practice is a very difficult question, and one which is the content of much of research at the moment. For example, the Maze architecture is one architecture which in particular is inspired by building up a better I-hash, a better fingerprint for different neighborhoods by using higher body features.
Yeah.
Okay.
So right now, what you're saying with the node coloring is really hypothetical. Like hypothetically, if we did that in a way to totally preserve the information, it is possible.
Yeah. So these tests are theoretical tools. So, like much like WL, this is a test which is supposed to be an upper bound on what it basically asks the question, what's the best possible geometric GNN that you can build? And the best possible one would be able to perfectly identify neighborhood fingerprints.
And for finite neighborhoods, so if you have a finite data set where my node can maximally have n neighbors and so on, then you can actually make bounds on how high do you need to go in the body order and so on. How high do you need to go in the tensor order? In principle, if you could have adversarial graphs with arbitrarily many nodes connected to another node, then these I-hash functions would need to essentially go, for example, to infinite tensor order or infinite body order, potentially, to be able to distinguish any possible graph. But luckily, in the case of molecules, you can even make limits on what are realistic graphs to occur, because you cannot pack atoms closer than a certain density. And so you can actually then have limits on, for practical applications, what is, the highest complexity for which graphs. It is not known at the moment, for example, if you have neighborhoods of n bodies, whether you really need all of the n body features, whether there's a lower number of body order that you can use to distinguish all possible neighborhoods of n features. That's currently a question that I think is studied by a couple of mathematicians, actually.
Yeah. Does that somewhat help understand this procedure?
Yes, definitely from my side. And now we have another question in the chat. Where are the critical graphs coming from, so to say? Like, how do I know if they are relevant or representative of a class of problems?
Shall I take this one?
Yeah.
So it's a great question, and we'll have in the code base that Chaitanya is going to present towards the end of the talk, we have a couple of examples of these critical graphs.
Yeah.
And the idea is that we build up this code base for you to try out, essentially, whether the graph neural network that you've implemented catches those critical cases or not.
Yeah.
For your particular data set, it really depends on your data set.
Yeah. And I think just to jump ahead a little bit, right? All these synthetic examples or counter examples, essentially, they may often feel somewhat convoluted, but they often point to something really interesting that we maybe don't understand with our model or is a theoretical limitation. And I think that becomes a very strong basis to improving architectures and for future architecture design. As we'll show later, in fact, like those experiments are something we're very excited to share. Yeah. So just to recap quickly, right? So this test has two components, an invariant color and an equivariant blob called the geometric information or geometric subgraph that you grow at each iteration. So at each iteration, you're sort of growing the subgraph that you look at, and you're trying to color it. So subgraphs which are the same up to rotations are assigned the same color, and the ones which are not are assigned different colors. And that's what allows you to, for example, distinguish these two graphs, because after two iterations, you have a subgraph which cannot be superimposed onto each other. And so we define GWL, and GWL is essentially an upper bound on geometric GNN expressivity. And this is just directly following the results that we saw in normal GNNs. But this is interesting because it will now allow us to sort of characterize the theoretical limitations of geometric GNNs and say what they can and cannot do. Before we dive into that, we'll also quickly add a restricted version of GWL called Invariant or IGWL. And this version of the test doesn't grow the blob. It doesn't expand geometric information. It only updates the node coloring. So it only looks at local neighborhoods and colors them based on whether you can superimpose, rotationally superimpose them onto each other. It doesn't have that vectorial propagation. It doesn't have the propagation of geometric information. And the idea is to mirror invariant GNNs like Schnet and Diamnet, which compute some invariant scalar quantities locally at every iteration, but they're not passing on any vectors. And what you can see here with IGWL is that since you cannot now grow this colored blob around your central node, all the one-hop subgraphs in both these graphs are the same up to rotations. So your test would now assign the same color to each of them, and you'd not be able to tell whether the graphs are non-isomorphic or not. With that, we have all the tools that we need to give you a few results on geometric GNNs. So, for example, something that is somewhat obvious, but we were able to understand the mechanisms a bit better is the role of depth and how it propagates local geometry. So as we saw in the examples previously, right? We had these two graphs which are distinct up or identical up to one hop. So for every neighborhood, they're identical, but they're distinct when we consider two hop neighborhoods. And this allows us to actually precisely say what GWL can distinguish. So as we saw in this example, GWL can distinguish these graphs. We can generally say for any k-hop distinct geometric graph, and that k iterations would be sufficient to distinguish them using GWL. And we can conversely say that IGWL cannot distinguish graphs which are one hop identical because you cannot propagate geometric information, as we saw in the example previously. And these two results allow us to compare the expressivity of GWN and IGWL. We can say that GWL is strictly more powerful as it can distinguish more graphs. It can distinguish a larger class of graphs. And importantly, our framework helps us understand why. So given these two graphs, right, GWL builds this computation tree where you're propagating scalar and vector quantities from the leaves to the root. Interestingly, for IGWL, the point to note is that geometric information cannot flow from leaves to roots. So when you update the color locally, you can use geometric information, but you're not allowed to send geometric information across neighborhoods. And that's why the important point here is that invariant GNNs fail to understand how various one-hop neighborhoods in a graph will be oriented with respect to each other because they do not propagate geometric information. And that helps us understand deeply the limitations of invariant message passing and how they fail to capture global geometric properties. So we can say that these models fail to decide properties like the area or volume of bounding boxes, distances from centroids, dihedral angles, etc. And this is just a direct consequence of the results we showed previously. And that suggests how we can overcome these limitations. In fact, models already do, right? We can pre-compute certain non-local properties and use them as input features within our invariant GNNs. which is done rather successfully in models like GEMNet and SphereNet. Then we can also think about when invariance might be sufficient or a setting where invariance is all you need. So we can say that IGWL would have the same expressive power as GWL on fully connected geometric graphs, because you now don't need to propagate information. You can directly compute all possible invariants. And this somewhat supports the empirical success of graph transformers such as Graphformer, which was very successful, at least 1 year back, a very successful model across molecules and materials. So those were some results. We have more in the paper, but
wait a second. We have a point by Simon. Let's go.
Hey guys, I don't know if that's true. So like, I agree that they can theoretically be distinguished, but they do worse in practice, much, much worse. Even if they're all-to-all connected. Even if I have a small molecule with a large cutoff radius, everyone sees everyone. Yeah. So I don't think the all-you-need statement is like very precise, right?
Yeah. I mean, that's why it's a question mark. And of course, you know, even when you're operating on fully connected geometric graphs, right, the body order of scalarization would still play an important role.
Exactly.
So Graphformer, for example, was using only distances, which maybe are empirically quite successful, but we do know that there are several counterexamples of fully connected graphs where all the distances are the same, right? So certainly an equivariant GNN would be able to distinguish those fully connected counterexamples, but Graphformer may not.
But my point is, you know, you're making a jump here somewhat implicitly from being able to distinguish structures to actual performance. And I don't know if that jump is justified, right? Like sometimes two methods can
know, in fact, that it's like it is not, right? Distinguishing graphs is not all you need, but exactly. Is variance all you need? Like, I think here the question is, when is invariance all you need for distinguishing graphs?
Yeah,
I think here there's something that we need to understand between like the difference between the practical success and the theoretical limit that you can reach. And graph transformers have a theoretical limit that is much higher than the MPNN. But the problem is like, now we need to make them work, right? Because you add more degree of freedom, you add a bigger possibility of overfitting. You add more degree of freedom so you can better distinguish things, but you have more problem of overfitting. So you need you need to build things better, or to pre-train them, or to do something about them, right?
Yeah, certainly.
But Simon's point is super important here, right? For everyone listening as well. All you need, or distinguishing graphs, is exactly not all you need.
Yeah, no. Again, thanks for catching us on these very imprecise slide titles. I think we need to, you know, make these things tighter, certainly. I mean, all you need is just a reference to the original Transformer paper's title, right? Which is obviously not true, because attention was not the only thing responsible for the success of Transformers. But Simon also said that it's not true that fully connected transformer type models are highly performant, right? I guess Graphformer was a model that was a fully connected geometric GNN and was arguably rather successful, right? Like on small molecules, on OC20, on across several benchmarks, this model was performing very strongly. So yeah, I think benchmarks are shifting a lot though recently, right? So
Yeah, that's all fine. My point is just you can make a jump from expressivity to performance. That's all I was trying to say. But I think we're on the same page.
Yeah, makes sense. No, thanks for the great question.
To that point, like a very, very simple way of making expressivity practically infinite is to add a random number on each node,
Yeah,
right? But again, practically it doesn't do any good to do that. So there's we need to distinguish these two, definitely.
Yeah, I mean, certainly, I think like for us, the key perspective with studying expressivity often is just to repeat, like, where do the models fail, and then trying to improve where they fail. And I think that's a good bridge into the synthetic experiments, which basically are synthetic toy examples where we're trying to highlight, how all these theoretical questions that we studied actually materialize in practice, and maybe what are some practical challenges of increasing the expressivity of these models. And I do recommend you to check out the code base as well as sort of geometric GNN 101 that we have in there as well. I think it's been a helpful resource for beginners as well into this topic. So we talked a bit about depth and non-local properties. And theoretically, these tests assume that you're able to perfectly propagate geometric information with each iteration, right? But as Simon had said earlier, in geometric GNNs, you're stacking layers, and you're sort of computing these fixed sized features at each node, which may actually distort distant information. We know that it does for normal GNNs, but we wanted to see how that materializes for geometric ones. So we created this generalization of the example from the Payne paper, which we call K-chains. And here we know theoretically how many hops will distinguish these graphs. Essentially, you need to transport geometric information from the two ends to the center of the chain, and that would allow your model to distinguish them. And we train geometric GNNs with an increasing number of layers to distinguish these K-chains. It's a really simple task, but we already know that invariant GNNs like Schnedt and Daimnet will fail at this task. So this is something expected, and we do see that through our experiments. The interesting thing is with equivariant GNNs. So we know that if we set k equal to 4, then we need at least 3 layers to distinguish these two graphs. And we found that some models could distinguish them in that amount of layers, but others could not. And we noticed the same patterns, especially when you went to higher k. So instead of 4, if you went to 20 or 40, you'd see this pattern growing even stronger. And that's interesting because it suggests some evidence of over-squashing of geometric information across multiple layers, even for such a simple sort of task where you need to just transport some simple features to the middle of the graph. Then the second experiments focus on higher order tensors and what's the utility of sort of having these higher order tensors in frameworks like tensor field networks, NeckWhip, MACE, etc. So GWL perfectly aggregates equivariant geometric information, and that was that copy pasting aggregation. In practice, though, we wanted to see what could be some trade-offs between using Cartesian or spherical bases, as well as the rank of the tensor. So higher order tensors versus, say, Cartesian vectors. And to do this, we came up with the L-fold symmetric structures. So these are structures which do not change when they're rotated around an angle. So they'd have a period L. And what we did was we considered an equivariant task where you're given 2 distinct rotated versions of each of these structures, and you have a single layer of equivariant message passing, and you just look at the equivariant features at the end to see whether you can distinguish the 2 orientations of of these symmetric structures. And interestingly enough, here what you see is that layers which use tensor order L are unable to identify the orientation of structures with a rotational symmetry greater than L fold. So that means, for example, that models like GNN and geometric vector perceptron, which use Cartesian vectors, which correspond to tensor order 1, will not even be able to identify the orientation of very simple structures such as this, and of course would consequently fail at all these higher fold symmetric structures as well. In the tensor field network sort of framework, you are able to increase the tensor order arbitrarily, and you do so using the spherical harmonics, and that does allow you to distinguish these rotational symmetric structures. But there are obviously computational challenges, and you'd never use L equal to 5 or L equal to 10. In fact, using L equal to 3 is also something quite cumbersome in practice. And as we just stated, this issue of not being able to distinguish the orientations of neighborhoods is particularly prevalent for Cartesian vector-based models. And in the interest of time, I'll skip these experiments on body order. But
that's not in the interest of time.
Okay.
I'm happy to skip this, but let's get to a question from Simon or a point from Simon.
What are you doing in those images at the top? Are you just rotating it? Like, what's the shaded one in the back?
Yeah, so the shaded one is supposed to show you the other orientation. So, for example, you know.
Yeah, okay, but then that's a global symmetry then, right?
What do you mean by a global symmetry?
Well, in the leftmost one, it's a global rotation, right?
Mm-hmm.
So
yeah,
wouldn't your internal features just equivalently rotate with that? Like, what's the issue then?
Yeah, so you kind of feed this structure into any of these models, and you look at the equivariant features, and you look at the equivariant features for the rotated version, and they should be different, right? Because
they shouldn't be.
The internal
imagine there shouldn't be, right? Imagine this was a molecule, right? Imagine this was an extremely distorted water molecule, right? In a global symmetry, if this is all I have, I don't want these to be different.
Maybe to give an example. Shall I give an example?
Yeah, sure.
I can. Can you see me drawing on the slide? 1 second. So I agree with you that in this particular isolated case, where it is a global symmetry, I completely agree with you that basically we shouldn't be able to distinguish them. The idea is when you stack these together, then it starts to become interesting and to draw.
Then I 100% agree. You're saying once they propagate towards other parts.
Yeah, exactly. Okay, and that's why we want to. That's why we want to test this.
Got it.
Got it. Okay, I'll just draw one example, maybe for the people who didn't maybe understand it here. If we had a chain of, say, k elements again, and we now attach this wheel here to this side, and we attach the wheel at the same time to this other side, and we rotate these two wheels slightly with respect to each other, then suddenly it's not a global symmetry anymore. And now basically the question is, can our model identify the slightly different orientations and propagate them across these k hops? And that's why we have this task in the loop. But I agree with you, isolated, it doesn't make sense. It only makes sense in this context. Thank you for the question again.
Yeah, this is very useful. Yeah. Well, so is there an interest of time, or is there not an interest of time? Like, because there is more content, but well, let me quickly talk about it. The third experiment is based on body order and neighborhood fingerprints, and is based on the work of Sergei Pozdyakov at EPFL. So so there are these local neighborhoods that cannot be distinguished when comparing their set of k-body scalars. So for example, when you look at these two local neighborhoods centered at the blue node, all the pairwise distances, all the two-body features are the same, and you need three-body features to distinguish them. And Pozdenyakov's work is based on coming up with higher body order counterexamples. So there could be counterexamples for three-body and as well for four-body chiral and non-chiral environments. And so in our code base, we provide these environments, and you can take your geometric GNN and you can sort of test out whether your layer can distinguish these local neighborhoods. And what we see is that you require layers with body order k to distinguish the corresponding counterexample. So, as we had previously introduced, that Schnett is a two-body model, while DimeNet is a three-body, and Schnett is unable to distinguish the local neighborhoods in the previous slide for two-body. And we see this sort of pattern for other models as well. So to quickly conclude and provide the key takeaways, our work really helped us gain a deeper understanding of the geometric GNN design space. And we were able to categorize architectures along these three axes. I think it would be interesting now to look at other architectures in literature and fit them into this framework or figure out where the framework breaks. We saw the advantages of equivariant layers over invariant layers, and we also saw that building maximally powerful geometric GNNs today requires higher order tensors and higher body order of scalarization. In the full paper, we obviously have this framework with a few more general results, more details on scalarization body order as well. And importantly, we have connections with universal approximation. So there's been some works on universality of geometric GNNs on fully connected graphs, I should add, not on sparse graphs. But we kind of study how what's the equivalence between universality and this perspective of discriminating geometric graphs. And our results follow the work of Chen et al. And finally, in future work, we're obviously excited about this area and designing better models through the insights gained from GWL, as well as Geometric GNN Dojo, which is our code base. And thank you very much for attending. These are all our collaborators. Thank you to the collaborators, and thank you to everybody who helped in this work. And we're happy to receive your questions and feedback and discuss things.
Awesome. Yeah, well, then if people want to get into GNNs or geometric GNNs for the first time, I think probably this GitHub page of yours might be a good starting point. And yeah, thanks for the nice presentation and getting us a little bit into your paper.
Yeah.
Cool. Any questions from the audience? Tom, do you have any questions?
Yes, of course. Thanks a lot, Chaitanya, for the great presentation. Yeah, it's really insightful and really nice to finally see an organized way of looking at the expressivity of 3D GNNs. Now, like, I have a question though regarding like the expressivity. I know that, for example, if you give all the distances, like the pairwise distances, of the connected graph, the angles and the torsion angles, if I'm not mistaken, you can distinguish any kind of structure there. Am I mistaken or no?
Do you want to answer it, or should I answer it?
Feel free.
Yeah, so this is the point made by GemNet as well as SphereNet, right? That if you add torsion angles and distances, then you can completely characterize the degrees of freedom of molecules, especially, right?
Yeah.
And I think the caveat here is that torsion angles are a non-local geometric quantity. So then that obviously is different from our framework and what we can theoretically study around these local neighborhoods, you know, so like thinking locally, being injective locally, and then making results about the global perspective there.
Yeah.
Yeah,
So,
but that was what I was confused by. Sorry, can I quickly? That was what I was confused by. Was the Simon said that you were not only locally aggregating, right? And the bodies that we're aggregating across, they can be like 2 hops, 5 hops away. We don't care. So I don't really understand the value of this test or the new insights of this tests. Yeah, Simon, you can comment or.
Just on the previous question with the torsion angles and so on. If you want to use the torsion angles in order to increase expressivity, as it's done, for example, in say SphereNet or ComINet, the way you do it is for every local neighborhood, you need to define a reference frame. So essentially say which direction does something point. In a protein, you can do this very nicely because you've got the backbone. I think it's from N to C terminus. Protein biologists tell me I'm wrong. I think I always forget which direction. But you've essentially got a way that, you know, a canonical direction, and you can use this together with a side chain, for example, to create a local reference frame. And if you then have the torsion angles and the normal angles, you can say, okay, the next neighborhood is attached to me, you know, with this torsion at this rotation, and so on. And with this information, if I have those local reference frames, and those I always know, if you give me any neighborhood, I always know exactly how to orient it. Then I can stack together my structure, my geometric structure. The problem comes when I don't have a canonical orientation. And for molecules, that comes whenever you have symmetries. So when you have, for example, threefold rotational symmetry, which of the neighbors do you want me to take as the first, essentially, vector of your local reference frame? How do you call the ties? And essentially, that's where the difficulty comes in with these other two approaches. So what we call here reference-based approaches. The difficulty is how do you call the shots of defining basically what your reference frame is. And in our case, the GNNs that we study, in a sense, are canonical reference-based free, because we never ever have to define, you know, this is the standard reference frame that it needs to be attached to this neighborhood. And that's the main difference. That's also what Chaitanya meant with essentially non-local. So non-local doesn't mean here that we don't, or in our case, we do aggregate information from farther away neighborhoods. So we do get information of the 2-hop neighborhood, but only after 2 hops. We do get information of the 3-hop neighborhood after 3 hops, but we don't get it before 3 hops.
Okay, so are you saying that if we do the 2 hops GWL test that you propose, yeah, you should have added your name to that, like the Joshi Weisfeiler-Leman instead of having 2 names. But if you use this the GWL test, can you or not retrieve torsion angles in a hypothetical fashion?
You can, yeah.
You can. Okay, so the question, like you've explained a lot, like the differences and the reason behind your framework. But my real question was like, if with the two GWL test, you can find the torsion angles, and with the distance angles and torsion angles, you can define any 3D geometry. So is the 2 GWL test the upper bound limit that you would ever need in 3D space?
Well, so by 2 GWL, you mean 2 iterations of this test, right?
Yes, exactly.
Well, I mean, what the K-chains example shows is that, you know, you'd need more than 2 iterations to solve this. So for example, here, right, if you had more nodes here along this straight part of the chain, then you'd need more iterations. In this case, 2 iterations are sufficient because
I guess Dominique means 2 iterations of passing on geometric objects, and after that only passing on invariant objects. So I guess 2 GWL layers and then only IGWL. Is that the question?
Yeah, that makes sense to explain it like that.
Yeah, I don't know. Well, you'd still have the difficulty of kind of figuring out the local frames, or, you know, is it always true that having torsion angles, and distances is a complete sort of characterization of your geometry?
I don't know, like that's that was my question. That's how my question started. So if someone knows the answer, please raise your voice. But I think it does. Now the problem that you mentioned is the difficulty of finding that reference frame. But as you mentioned, like if you do just invariant aggregation after doing the 2 GWL test, then perhaps there is a way to get that reference frame and to distinguish them. So this would make possibly the 2 GWL test the upper limit of everything you would ever need in 3D space. But like we would need maybe someone else to step in and tell us their opinion.
No, I think that's a great idea, Dominique, actually. I mean, we haven't tried it, actually. But if you did 2 layers of geometric, you know, Weisfeiler-Leman type message passing, and use these 2-hop neighborhoods to now define an orientation rather than the 1-hop neighborhoods to define the reference frame for 1-hop neighborhood, whether that gives you complete expressivity, could be. I would have to think if there's counterexample cases. It's not directly captured by our framework, but it's a very interesting question, I think.
Yeah, I mean, the challenge would be that, you know, like if there is even one convoluted counterexample to this, then we can't sort of say things provably. Yeah.
And a counterexample would come from something where you have rotational symmetry, essentially after the 2 hops.
Yeah. But I guess if you are able to find literature perhaps on the uniqueness of 3D geometry defined by torsion angles, and distances, that would solve the problem.
Yeah.
But anyways, I don't want to spend too much time on that particular question, but yeah, it'd be interesting also to see in 4D, like, is 3 GWL the maximum you need? In 5D, is it also? But yeah, now we focus on 3D, which is the most useful case anyways.
Yeah. Maybe just one word of caution, I think, because the waters of geometric graph neural networks can sometimes be a bit tricky to navigate. There was also this very nice paper on scalars are universal, where I think basically you only need the all-to-all distances. And you can show that you can reconstruct the entire geometry from all-to-all distances. You don't need angles, you don't need torsion angles, and so on. But the caveat with that work is you need to know which distance goes where. So you need to know exactly, basically you can't do the aggregation step in a GNN, which loses, because of the permutation invariance, the information which distance came exactly from which node. And so that really is what makes these things tricky. So I wonder actually if you have distances, angles, and torsion angles, it passes the fire test of permutation invariance.
Well, I think for the distances, it's only a question of reflection. it uniquely defines two possible geometries when you have all distances. The geometry itself and the mirror image of that geometry.
I mean, it defines the geometry up to rotations and inflections, yeah. So up to operations of O3. It uniquely defines the geometry.
Ordering, right? Like it can't be the unordered set of distances.
Exactly, yeah. You need to know which distance.
So like the paper says scalars are universal if you have the ordered set of distances, except that graph neural networks never have the ordered set of distances.
No, I think the distinction here is are two different ones. One is the one is universality, and one is it universal with respect to S E3 or only with respect to E3. And yeah, also I'm pretty sure on the other point about the other point about torsion angles, distances, and bond angles, like one-hop distances and bond angles. From the theorems in the GenNet paper, I'm pretty sure that it's not the case that you like have the power to distinguish, or well, let's not talk about. You have the same representational power as a high order tensor field network.
Yeah. The GemNet and tensor field network proofs are also for full graphs, so fully connected graphs or point clouds. So there's also that caveat to those results around universality.
Okay, I'm not sure what you mean there, but anyway. So I would be happy to continue discussing this point or to move on to other questions. What do you think?
Let's move on to Ladislav, perhaps. Yeah.
Yeah, whoever like to unmute themselves and ask.
You did. Okay, we can't hear Ladislav for some reason. Then Ladislav, maybe you can figure out why we can't hear you. And meanwhile, yeah.
Oh, sorry. Excellent. Thanks a lot for the great talk, and sorry for the mic issue. So it's a lot of the questions that I had were just answered, but I'm still want to like confirm, like when you think of the GWL, do you think of it as convergence in as many steps as you need to take until you converge to the same colors and you have the entire graph? Or why not to then really have that kind of hierarchy as what was Dominic talking about, where it would be equivalent to something like that KWL hierarchy? Because right now it feels like your GWL is really like the n order GWL, so to say, and it feels like it's way too powerful, that it gives you this upper bound, but it doesn't feel like it's very interesting to actually study something, because it's just this idealized case, but doesn't really distinguish any models, right? So like, don't you want actually some kind of a hierarchy? And this GWL, the way it sounds, it might even be as powerful as simply being able to distinguish isomorphic graphs. So in that case, it's a little bit unrealistic, right? So what is your take on that? Or whether I just understand it not quite correctly? I would want, that is at least my take, I would want to see a little bit more distinguishing power than just taking something that is omnipowerful and can do that.
Yeah. No, I mean, I think that all those points are really sensible. So we do have variants of this test which we didn't present but are in the main paper, which particularly study the body order of scalarization. which allows you to build sort of weaker and weaker versions of this test and match architectures with that body order onto them. So, for example, well, I guess, yeah, we didn't present that part today, but that is in the paper, like weaker versions of the test, essentially. And you're exactly right that, the most powerful version of the test just seems like an upper bound. And it's actually the tests which have some limitations that actually highlight interesting modeling points, right? So we do somewhat accommodate for that in the paper. And then regarding like whether this test can directly solve geometric graph isomorphism, right? I think it's something that is hard to prove in the general case. But we did say that this test is very powerful in the case that you operate with realistic geometric graphs where the neighborhood is defined as a function of some radial distance, which is usually the case for atomistic sort of systems and atomistic modeling. Yeah, and I think
yeah, but if you're aggregating the entire graph into every node, and at the end of the, like if you stack as many layers as you need, then you have the information about the entire graph in every node. And if you assume that you have this magical hash that can just distinguish anything, then obviously it's like equivalent to having like n order WL in normal graphs, right? Like you just simply at that point you're relying on the hash being able to do isomorphism testing, right? Like you just packaged everything into the magic of the hash. Isn't that the case?
Yeah. I agree, and that's why we studied like versions of the test where we consider weaker hashes essentially.
To draw the connection to classical WL, if you were to place all of the coordinates of all of the nodes at 0, so if you basically collapse the graph into the origin, but you keep the relational structure that you had before, then it would actually be equivalent to 1 WL. If you say we have a radial distance cutoff graph and you collapse all the nodes to 0, obviously if your radial distance is larger than 0, then it would be a fully connected graph in which case 1 WL. The one-hop neighborhood would be the entire graph already.
Yeah, so I guess like the answer is that there are nuances, yeah, which we may not have presented sort of fully, but it is in the main paper in a bit more detail as well.
And in a sense, the coordinates also work as a way of positional encoding. If used in accordance to their symmetries, they're essentially a positional encoding for the message passing, which is why this 1 WL version in the geometric setting is or seems so much more powerful than the 1 WL setting in the non-geometric version, where also usually you don't have a positional encoding.
Okay, I'll check out the paper and see like how the hierarchy can actually look like. Yeah, sounds interesting. Thanks.
Thank you.
Yeah, thanks for the great questions. There's Konstantin who had a question.
Yeah. Thanks for the talk. I have some combination of statement and question. So if you know there is an result for classical WL test, which is kind of calls back and forth between what you had when you limit the capacity of the context that you consider in GVL. So say if you consider not the whole graph, but only several hops, you cannot distinguish long flipping chains, right? And similarly, not all graphs can be distinguished with WL test. And for the most parts, if we say that, fingerprints are the same, that's the same graphs. And if we have only one graph, usually we can say nothing about it. But if for the said graph, it's for its stable coloring. The flip graph is a bouquet forest. We can tell that said graph is uniquely identified globally among all the graphs.
Sorry, can you repeat the last statement?
So if for the stable coloring of a classical W test of the graph, its flip graph is a bouquet forest, then we know for sure
Its
for
flip graph is a what?
a bouquet forest. Bouquet is like 5 trees, one designated node in each tree, connected in 5 cycle, and bouquet forest like different bouquets plus some trees.
Okay. Yeah.
So if that happens, then we know for that original graph for sure that such coloring and consequently classical BL test uniquely identifies it. So there is no other graph exists that has such coloring at all, which is somewhat unique for BL test, because usually we can tell only for the paired graphs whether they are the same or not, and not one versus everything. And I was wondering whether for GWL process we can get some sort of the same result, even for incomplete one. So obviously, if we have all capacity in the world and we consider the whole graph, most likely that is the case. But what if we consider only say 2 hops? In the context, would there be a way to place a condition on resulting coloring that says, yeah, that's enough. With this one, we can distinguish one graph against everything else.
So essentially characterizing the graphs. So saying for this graph, I need at least this type of model to tell it apart from every other graph.
Right. I mean, this question is mostly in connection to molecular graphs, right? Because from my perspective, okay, we have all these molecular data sets, and for the most parts, we can say, okay, even classical BL is enough to distinguish it, and independent works. But what if we add coordinates of atoms? Can it be that for everything we know about molecules, in the public domain so far, models that consider geometry, even weaker ones, are actually already enough?
And the simple answer is we don't know for the geometric setting, but it's a very interesting question.
Yeah.
And I'd be curious to know the answer as well.
Yeah, I think like, so geometric graph isomorphism problem, right? I mean, I don't think we are the first to define this, but we defined it specifically for the context of these geometric GNNs. But I think these kind of problems have been defined previously or have been studied in other contexts. I don't know how to answer that question, but that was interesting to hear that. Like, I also didn't know a lot of these things.
Yeah, and if you don't mind, there is a second part in concern to the molecular graphs. So there is other results that says that for planar graphs, it is enough, and I mean topological graphs, of course. It is enough for dimensional VL test, or for other forms with no 3-dimensional folklore VL test, to distinguish all planar graphs. And because most organic molecules, except for handful of walls under planar graphs, we sort of care about it. But then it appears, okay, this whole proof on for VL depends on the composition of the graph into two connected and three connected components.
Mm-hmm. Yeah.
And from perspective of geometric, well, it kind of begs this question. Okay, if it's two and three connected components, can we sort of get away with what is four body interactions plus logarithmic number of layers?
Mm-hmm. Yeah, so I again didn't know that result on planar graphs, and 4 WL and 3 folklore WL, did you say?
Yeah.
Okay. But yeah, I mean, I think there could be some ways to draw connections to this geometric graph setting as well, especially if you make certain assumptions about how these geometric graphs are created. Like I know that planar graphs also have some definitions, right? And again, similarly, like we maybe have to make certain assumptions about the definition of these geometric graphs. But that sounds like a very interesting or relevant result to try to translate to this setting as well.
Oh, and the last one. So I think this list of authors, Christian. And because of that, I was wondering whether there were any tries to apply the theory of this paper to cellular networks.
Yeah, so I think like with simplicial complexes and cell complexes, I mean, one could imagine porting those techniques to geometric graphs as well. I think they're a very cool way to incorporate hierarchies, right? Or like higher order interactions among multiple bodies, multiple nodes. Yeah. I think all those are like, all the things you mentioned are super interesting.
Well, thanks. I hope we can get more into the stuff.
Yeah.
Thanks also.
Yeah,
Thank you.
Okay, awesome. Then I think we have no more questions left.
There's one in the chat,
yes.
which actually is something we can quickly talk about. It says, how performant are higher order tensor equivariant networks compared to invariant ones, especially in terms of data efficiency? I think people have empirically seen that tensor equivariant networks are actually more data efficient. So Simon Batzner and others' work has shown this, that for certain benchmarks of interest, the learning law or scaling law of these equivariant networks is much steeper, which means that they scale better, or they require fewer data to reach the same performance. I think it might depend on the data set of choice, or also, I think it's quite an empirical question, but I think also important question for the community to think about, actually, like why do these equivariant networks have better scaling laws? Or I think our work sort of helps us understand why we need these higher order tensors, but I think there's certainly more interesting points there to think about.
Mm-hmm.
Yeah.
Okay. Then I would say we've come to an end here, and we can say thanks for all the nice questions and thanks for the presentation. And do you maybe want to have some last words before we call it a day?
Yeah, thanks for all these super interesting questions and for everybody who tuned in. I mean, I think like certainly got so many new perspectives on this field. And also thank you to Hannes and Dominique for creating.
Oh, wait a second. We have a last second question, I think, from Amit Roy.
Yeah. Hello. I would like to know one thing. It is you guys are talking about the expressivity of graph neural networks and these things. So I would like to know, as a young researcher, that how important is it the expressive power of GNNs for different type of tasks, like for node classification and graph classification, and for other type of tasks like anomaly detection or outlier detection?
Yeah. So, I mean, I think people have very opinionated responses on how important is expressivity. I mean, and I think Simon can give his perspective, but my perspective on expressivity is that it tells you what's the best possible thing your model can do. You know, it gives you these best case scenarios in the ideal setting, but it also tells you where your model fails or how your model is failing. And I think that's really valuable for architecture design and for really understanding our tools in a deep way. I think that's the value of sort of studying expressivity.
For me, it's kind of a lower bar, I would say, because if the model can't even distinguish, then there's no chance it can predict two different values, essentially, for two different data points.
But I'm wondering, like, doesn't it depend on the downstream task also? Like, do all of different tasks expects your model to be distinguished? I'm just wondering about this thing.
I mean, of course, like in some tasks, if you have two graphs that are where it does not matter if you can distinguish them for the property that they exhibit, and that property is what you're interested in predicting, well, then it does not matter.
Yeah.
But it does if it is important for the property you're trying to distinguish, then yeah, you need to be able to distinguish the graph. Otherwise, you
I
make
think
the
also, yeah, I think it's not only about distinguishing the graph, but also sometimes like subgraphs can look very similar to some models, but very distinguishable to others. So that even if the WL test will tell you you can distinguish these, the question is like how easy it is to distinguish these from the model perspective, and then the task that you have at hand. Does the task that you have and that you require needs you to be able to differentiate a lot these things that appear the same under certain lenses, or they don't need that? So like it's always a question like, are things that look the same, should they also behave the same? If yes, then a weakly expressive GNN should be sufficient. If no, if you have like in the case of chemistry, you can have activity leaps that change a lot when you have certain changes that are not distinguishable, then you need more expressivity. Now to go back to molecules though, as soon as you have 2WL, it's enough. You don't need more than that because they are not complex graphs. So you always have to look into the lens of like, should I be able to distinguish things or not, and by how much?
Thank you for the explanation.
Also, maybe if I can quickly, hey guys, by the way, if I can quickly get into this, you're referring a lot to expressivity in terms of like the input you encode into the model. For instance, like Schneck only uses distances and DimeNet only uses distances and angles. So it's not sufficient to distinguish between a certain set of molecules. But you haven't talked a lot, I think, about the expressivity of GNNs themselves. So if you use like higher order features, it's great. But if your aggregation function is not injective, that you may not be able to distinguish between two types of graph, although you have a different input set for two graph, right? So maybe my question would be, have you tried a bit to correlate this expressivity, which is like a super interesting discussion, not only with maybe the input features of each graph, but also with like the message passing of each graph, which is a big limitation, but it's not core to geometric deep learning. I guess it's core to GNNs as a whole field.
So So if I had to rephrase the question, it's saying that, we tried to frame one of the axes of expressivity as body order, right? Like how many nodes are involved in computing scalars, so distances, angles, and so on. But what about, so then you have this multi-set or set of distances, angles, scalars in your local neighborhood. What about the sort of practical aggregator that's applied on that multiset? That aggregator has to be injective itself, right? Is that what you're kind of thinking about?
Yeah, definitely.
Yeah, I think generally, like generally you're given a set and you need to injectively aggregate from this set. Now the members of this set are continuous, right? Like they're not discrete, like these are scalar values. So then if you look at the sort of universality section of this paper, then towards the end, we discuss how our results and discrimination perspective is connected to the principal neighborhood aggregation paper, which studies exactly this setting, right? That you have these real valued multisets and how do you be injective over them. So there's certainly like interesting links even to like that line of work on how do you actually build injective continuous aggregators as well.
Which in our formalism is essentially this I hash, this idealized I hash. So I completely agree. I mean, how do you actually instantiate a good version of this I hash for a practical model is very much an open question.
And I think it's the main question at the moment, because most methods now manage to extract meaningful features, which can like use, and there are enough uniquely identified graph. And the main strength of the GWL that you construct is this injective hash function, which takes the structure which is unique to like a unique value, unique coloring. And I guess the real question is how to, can we ensure that we get injective maps, or can we get close to it? Or in a way, maybe, because I guess this will be the real challenge. And that's maybe why Maze fails to distinguish two graph while it could theoretically, because just the structure of the graph neural network cannot cope with such complexity.
Yeah. Yeah.
And maybe on the same topic, you said that invariant graph neural network, they cannot pass geometric information. And I agree in a way, but what if you have an injective function from like the 3D geometric information to an invariant representation, which is sort of what GNN manages to do with this extraction of torsion angle, I guess. So this would enable to pass geometric information, right?
Yeah, I think this is exactly what we mean by these canonical reference frames. So if a canonical reference frame is exactly that. It allows you to take geometric information, and then you can project on the axis of this canonical reference frame, and then there will be scalars. The difficulty then is how do you get the canonical reference frame? You could base it on the global structure, you could base it on the neighborhoods, but I completely agree. So you can pass geometric information via invariant channels, but if you do that, you need to define a canonical way to orient either neighborhoods or the full graph. You need some sort of canonical reference.
Agreed.
So it's like if you're coming from physics, it's kind of like a local or global gauge field that you need across space, essentially.
Fantastic from my side. I can only say I really enjoyed this. Another lovely discussion with many active participants. And if you want to join the reading group sessions yourself and also be an active participant, for which I would love you very much, then all the information to do that is in the description. See you.